Hello. Still on video. Hey guys. What's up? Okay. Just pull up stuff from Google Classroom.
Oh, nice.
Okay. Happy Amazon Prime Day. Any of you guys get any good deals?
There's some compression shorts, but I can't get them because I don't have Amazon Prime.
Oh no. Yeah, I heard Walmart is trying to compete and have their own like sale day. So maybe it's on Walmart. Okay. So today I just want to basically go over homework, maybe cover, and also maybe expand a little bit. I realized when I covered the multiplication rule, I kind of forgot to, or it would have been a good time to delve deeper into that idea a little bit. I did it a little bit out of order how they do it on Khan Academy. But first I'd like to kind of do those problems from, what is it called? Mathopolis or Math is Fun. So I want to go over them and see, if you guys had any questions on any of those about the Bayes' theorem. Let me see here.
For the Mathopolis questions, do you want our work on like a piece of paper
Yeah.
for those? Okay.
Yeah, if you can do them separately on a piece of paper, that's really good. And were there any questions on those? Let me see. That you guys wanted to go over carefully, or did you feel pretty comfortable with them? The last time I taught the class, there were quite a few questions from those Mathopolis ones. So any of them that you want to see or go over? Okay, yeah. If you haven't started yet, we can also discuss them on Thursday as well. So I definitely recommend focusing on that for the homework. That's a really good. Oh, the Mathopolis questions. Let me just they're under the assignment, on the homework assignment. I could just share my screen here. Google Chrome. Yeah, let's go over them on Thursday. It looks like some students haven't gotten a chance to do them. So they're over here. on homework 4 on the link. And then there's a collection of 10 questions that I think are all pretty good. And they shouldn't take too long, but the later ones, maybe just have to set them up carefully and think about them. So let's plan on Thursday to I definitely want to go over these and make sure that, you know, if there were any questions that you guys have them all cleared up. But this is a really good practice for Bayes' theorem. Okay, so let me then go over some of the questions that I didn't actually introduce about what we could use the multiplication rule for with independent events. So let me share my screen. Okay. So this is applications of the multiplication rule. Independent events. And possibly, I think we'll have time to talk about binomial probability. Oops. All right. So last time we saw that if you're doing something like flipping one coin after the other, or something that's just told to be independent, the condition for A and B to be independent, so A and B are independent events, if and only if probability of A and B equals probability of A times the probability of B. So we saw this last time, and we saw that the multiplication rule really comes from setting up the conditional probability of A given B just equal to probability of A. In particular, you can extend the multiplication rule the multiplication rule to the intersection of multiple mutually independent events. So so this tells us that the probability of A and B and C, for example, is equal to probability of A times probability of B times probability of C. And you can set this up, you know, you can justify this by saying, well, if A is independent with B and B is independent to C, then A should be independent of B and C. And then you can kind of go from there. And so this is useful for questions like the following. So you have a jar. So here's an example. So a jar contains 5 red marbles and 2 green marbles. What is the probability of drawing, and this is a key phrase, with replacement red, green, red. All right. So what do you guys think? And you could raise your hand if you just want to say the answer.
Do you just do 1 out of 5 for the red, and then times 1 out of 2, and then times 1 out of 5 again?
Okay, good idea. Not exactly. So what's for the first draw to get a red? What's the actual chance of getting a red?
Oh, sorry, it would be 5 out of 7 times 2 out of 7 times 5 out of 7.
You got it. Nice. Yeah. So 5 out of 7. If it was a specific marble, then it would be 1 out of 5. But here's 5 out of 7 times 2 out of 7 times 5 out of 7. And here I'm being specific about drawing it in this order. So in this specific order. Excellent. How would it change if I wrote this problem, if I said, what about without replacement? How would these things change?
Wouldn't the denominator begin to change?
Excellent. And not just the denominator. Oh, by the way, this is probability of red times probability of green times probability of red. We break it up all into the first ones. Yeah. So how would it change?
Would it be 5/7 times 2/6 times 4/5?
Excellent. And who was it? Was it Alex or Becca?
That was me, Becca.
Hi, Becca. Yeah. So how did you get the denominator changing and the numerator changing?
Okay, well, you start because there's 5 reds and then there's 7 total. And then if you pick one of those and then you don't replace it, then you have 6 left. And then there's 2 green. And then if you then pick another red, there's 4 red left, and then there's 5 left in the jar.
Oh, excellent. Yeah, sorry. That's excellent. Awesome, Becca. Thank you. Yeah, so as you're picking them without replacement, your denominator gets smaller, but also your numerator, if you're talking about picking from that same color again, that also will decrease. When you pick without replacement, are you allowed to, are those events of getting a red after you've already picked some other, after you picked a green, let's say, are those events independent or dependent?
They're dependent because they're changing from the actions of the prior numbers. So from the first, from 5 out of 7, you can tell that they're dependent because it's changing. The denominator changes because of what you did in the first move.
Excellent. Perfect, Jeremy. Yeah. So the probability of red is no longer 5 out of 7 for the last one. It's because of picking red and then green, it's now changed to 4 out of 5. So whenever you have these draws without replacement, you're clearly affecting the probabilities as you're drawing. We'll actually talk a little bit about this in the context of like very large samples. If I told you, so just kind of going to a little bit about statistics, which we'll get into later, but imagine instead of like 5 red marbles and 2 green marbles, imagine I told you you had 50,000 red marbles and 20,000 green marbles. Do you think that they would be essentially independent? If you asked what's the probability of red, green, and then red?
I mean, essentially, but would they really? Because it still changes.
Exactly. They're not, by the mathematical definition, definitely not independent because it changes slightly. But the idea is if you're doing some approximations and estimations, you can assume for all intents and purposes that you can estimate, what would I say, 50,000 over 70,000? The next one would be, what is it, be 49,999, and the other one, the denominator would be 69,999. So that number would be really, really close to 5 out of 7. So if you're trying to calculate stuff for statistics and you have a really large size sample set that you're drawing from, we sometimes just kind of make the assumption that the draws are independent, even though they technically aren't. So that's something to be aware of. In statistics, we almost always make the assumption that each survey response that you get or each question that you get answered is independent of the other, which is very questionable at times, but sometimes it's okay to make that assumption. So very good. So these are not independent, clearly not independent. But you could still use the multiplication at each step to, what we're really thinking about here is actually, you can visualize it as a tree diagram, right? You have 5 red, 2 green, and then based on what you picked, the tree diagram that you can draw will look a little bit different. So I'll just highlight here. Okay, very good. Any questions on these 2 examples? Okay, so now I'm going to do another one. So this is, by the way, the phrasing here is what's the probability of a red for either of them is a red and then green and then red, right? It's a specific sequence. What if I ask instead something a little bit different? What's the probability and this time it's going to be with replacement. Same thing. What did I say? 5 red, 2 green. What's the probability with replacement of drawing exactly exactly 2 red and 1 green. So think about this one a little bit. You guys have the tools to answer this. And when I say exactly 2 red and 1 green, I mean you're going to have 2 red and 1 green, but you can draw them in any order that you want. Is it? So okay, so I'm getting some different answers. I'm just going to ask the students who messaged me how they got it. And if you're not sure where to start, think about the different ways. Like we saw how to get like red, green, red. But what are the other ways that can happen to get 2 reds? That's only one of the ways. So it's very similar. It's very similar. Let me kind of scroll up here. It's very similar to the first one. And this ties in really, really closely with what we learned before about rearranging letters and counting ways to rearrange letters. By the way, what is 7 to the 3rd power? What is that going to be? 343. Thank you. So this number here is 25. The numerator is 50 over 343. So the probability of drawing exactly 2 reds and 1 green, maybe I shouldn't say, maybe just say like in any order. Maybe I need to add that in. And the reason I say is exactly is because sometimes that, nice. Lasha, do you want to explain your idea?
Sure. So what I did was I got the probability of drawing 2 red and 1 green in one order, which was 50 over 343.
So let's say probability of red, red, green is 50 over 343.
And there's 3 ways to do that. There's what? RRG, RGR, GRR. We know that because it's 3 factorial divided by 2 factorial.
Nice.
So we just do 50 over 343 times 3.
Perfect. And do you see that each of them has the same thing, 50 over 343, because they're all independent and doesn't matter what the order is, like to get that number 50 over 343. It just depends on how many G's you have and how many R's you have. And they all have the same.
If we had that same question without replacement,
Uh-huh.
Would it be like reset between them? Would like RRG be 40 over 210, and then like would RGR be different than that?
Good question. What do you think? Anyone have a response?
I think all you would have to change is like if you find the like 3 different fractions for each, that's what would change, but you'd still just multiply it by 3, I think. So like if the fraction for 50 over 343 is like 5 choose 7 times 5 choose 7 times 2 choose 7, but that's what you would change, like what we did up above when there's no replacement, instead of like when you change the denominator. But I think you would still multiply it by 3 because there are 3 different options.
Yeah, and what's interesting, what logic kind of is hinting at is like, well, if I change the sequence, red, red, green, or red, green, red, yes, the order of things will change. So like it'll be, if it's with replacement, and you can come up with a nice argument here. This is, just 5 out of 7 for, let's do red, which one did I say? Red, red, green. And instead of being 2 out of 6, it will be 4 out of 6. And then the next one will be 2 out of 5. So the order, the denominator will always be dropping down by 1. And the numerator would be declining by 1 for the number of colors like that you're drawing from. So that it will be 5, 4, and then just a 2, because you're only drawing 1 green. But the idea is that even if you change, the denominators will have the same order, the numerator might be shifted around, but it's going to be always the same number. What is that? 40 over 210.
It is always going to be the same number?
Yeah. Do you see why?
Oh, yes, I do.
Nice. So regardless of with replacement or without replacement, the idea is that you can calculate one specific sequence and then multiply or add them together for the different ways that you can achieve a collection of the marbles. So 2 red and 1 green, and we know that there's 3 choose 2 or 3 choose 1 ways to rearrange 2 reds and 1 green. Okay, let's do a similar one. So, so this time, parents have a 50-50 chance of having a boy or a girl if the parents have they have 4 kids or 4 children, what is the probability of 2 sons and 2 daughters? And of course, when I just say like some quantity of each type of child, I don't mean, I'm not talking about their order. They can be in any order. And so you now have the tool to answer this question. If you think carefully about the last example, it's actually identical to the last example, just the numbers are a little bit different. All right, you guys are sharing some really good ideas. Kieran, do you want us to share how you did it? You can also annotate on this if you want.
I am not sure I'd be able to do that particularly well, but I'll try and walk through my process.
Yeah.
So I did think of it in exactly the same way as the other one, but first I thought of like what the probability of just having 2 girls and 2 boys is, generally speaking. And so by kind of just multiplying all of the probabilities together, so like probability of, yeah, girl, girl, boy, boy, is going to be the same as probability of girl times probability of girl times probability of boy times probability of boy. Which would be 1/2 to the 4th power.
Nice. And we're making an assumption here, which I don't know if it's actually true. I think it is, but assuming that having a girl or boy before doesn't affect your chance of having a girl or boy after, which might not be true because there's like the thing with Henry VIII, right?
Maybe. Yeah, like, I'm assuming they're independent.
Assuming they're independent, which I also assume, but there's some weird things with genetics that might make that not exactly true, but let's assume for all intents and purposes it is. This would be 1/2 to the 4th.
Yeah.
Excellent.
And then just like Anjanea did, or Anjanea, just like Lasha did, Anjanea is a really cool person, Lasha, by the way, so being mistaken for him is great.
Thank you.
But like what Lasha did, I just thought of the possible combinations of GGBB, or not combinations, permutations of GGBB.
Permutations, yeah. Yeah, either way.
Yeah, the variations or whatever.
Nice.
And so then that's just 4' over 2', 2'. Exactly.
The number of ways to rearrange 2 types of letters, 2 of each types of letters is going to be 4 choose 2, or if you're doing the Mississippi problem, 4 factorial over 2 factorial.
Yeah.
So this is just going to be equal to 4 choose 2. So the overall probability of 2 girls and 2 boys in any order is, you have to add up this expression 4 choose 2 different times. So it's 4 choose 2 times 1/2 to the 4th. And what is 4 choose 2?
It's just 6.
6, nice. So 6, and then 1/2 to the 4th is 16. So this is going to be, yeah, 6 over 16. By the way, what do you guys think? how does this compare to 1/2? Because like if you ask most people this question, a lot of people will just kind of right away say, oh, it's 1/2 because 2 girls, 2 boys is half and half. So how does this compare to 1/2, and why could we have, well, what's the intuition for that?
Don't they begin to add up, or it's something relating to that? Just because it's like as you add up, like the after the first kid, there's going to be a different. I can't explain it, but I have like that idea of it's like it starts to change as you get to like the second and the third child.
Well, the probabilities of each kid being a boy or girl stay the same, but yeah, the probability of having them half be boys and half be girl does start to change. Can anyone explain kind of what's going on here? Quentin, go ahead.
Yeah, it's slightly less than half because the way I think about it is if you look at a simpler example, if you just had 2 kids, right?
Yes.
There's one way to have 2 boys, there's one way to have 2 girls, but there's 2 ways to have a boy and a girl. So generally speaking, if you're having multiple of the same, it's going to be less likely than having different ones. Wait, no, that doesn't actually work. Never mind.
Yeah, okay, so in that example, having one of each is 50%. But yeah, why is the percentage dropping here? Less than 50. Is there kind of like a nice visual way to explain why that kind of makes sense intuitively?
I just kind of, and this might not be exactly the correct way or anything, but I kind of think of it in like, as you start adding more events, the probability of like the events occurring like in the exact way probabilistically they should kind of diminishes. Like when you add more factors, things start to get more chaotic almost. I mean, that's more pragmatic and less theoretical, but it might apply in a similar way.
No, Kieran, yeah, that idea is exactly right. So like imagine, you have 100 kids. What's the chance of them being exactly 50 boys, 50 girls? Yes, there's lots of rearrangements. 100 choose 50. That's a pretty big number. But still, you'd agree that that's not like, you're not like likely 1 out of 2 chance to have 50 boys, 50 girls. There's so many other possibilities. So the one way to visualize it is with the tree diagram. And this, you can actually visualize this whole thing with the tree diagram, right? You can have boy, girl, boy, girl, boy, girl, another boy, girl, boy, girl. Okay, it's going to keep going. And it's going to have 16 branches. And there's a lot of branches that are not, don't have 2 boys and 2 girls, because now you have other possibilities. You have all boys, you have all girls, you have 3 boys, 1 girl, 3 girls, 1 boy. So there's so many other possibilities now that it starts to diminish the possibility of having exactly a 50-50 boy and girl. Okay. So that's a nice intuition. And now let's do another follow-up question on this, just to kind of see how you can extend these ideas. Any questions on any of this? This is a good place to ask. And if you're not sure about anything I wrote down, or please hit yes if you feel like this makes sense, and how it connects with both independent events and the stuff that we learned previously with the rearranging, talking about number of rearrangements and using combinations. Okay, great. Yeah, jump in. If any part of this is weird, just jump in and ask me. Okay, and
the tree prove that it's not exactly 50-50?
Yeah, so the argument is so for 4 kids, it is, sorry, no, if you have 2 kids, the chance of having boy or girl, like 1 boy, 1 girl, is 50-50. And for 1 kid for 1 kid it's not 50-50. For 1 kid it's 0, it's impossible. But as the number of kids that you're having grows, if it's an even number, it actually becomes a lower and lower chance of being 50-50. Just because there's so many other possibilities. That's how you could think about it.
All right, thank you.
Okay, so here's another type of famous question related to this one. So let's say a family has 6 children. What is the probability that they have at least 1 girl? This is a really famous type of problem. You might encounter it on the like a standardized test, like a GMAT or GRE, or I don't know if they have it on anymore on the SAT, but this is a nice problem to know. And there's a long way to do this, which is good, and there's also a shorter way to do it. Olivia, do you want to share your idea?
Yeah, sure. So what I was thinking of is that if you do 1 minus the probability that the family has no girls, that would get you the probability that they have at least 1.
Awesome. So probability of at least 1 is equal to the complement. So the opposite event of at least 1, because you have 1, 2, 3, 4, 5, or 6. But the other thing that you can't have is no girls. So that's probability of no girls. And Olivia, what would the probability, why is that a nice number to calculate? What is that probability?
I'm not exactly sure, but I just feel like it would be easier than, it's only 1 event rather than like a lot of events to calculate.
Excellent. And let's do it together. So no girls means boy, 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 boy. So what's the probability of boy after boy after boy after boy after boy if each thing is 1/2?
One 1/64th.
Nice. Yeah, this would be 1 minus 1/2. And you just raise it to the 6th power because you have the 6 terms.
Why are we doing 1 minus the, or what, 1 minus 1/2 to the 6th?
Yeah. Do you see that these events, at least 1 girl, is the complement event, or is like the exact opposite event of no girls? Like, remember in complement, like when you roll a die, if I say what's the probability of getting a 1 or a 3, the complement would be getting every other number. So the probability of an event and its complement, they always add up to 1. So sometimes it's easier to count the opposite event and subtract that from the total, or from 1.
I have a question.
Yeah, Quinn.
What is the long way to do this? Because you said there's a short and a long way. Or is this the long way?
No, this is the shorter way. Yeah, I'll show you the longer way. We can think about it in a second. But Alex, did that make sense with the complement?
Yeah, it does.
Cool. And we talked about the complement not in terms of probability, but we talked about the complement in terms of counting like configurations when like it was the cars that were parked next to each other. And it would turn out to be easier to think about the cars that were, what was it? We wanted cars that were not parked next to each other, but it was easier to just take all the car arrangements and take away the cars that are parked next to each other. So it's the same thing. Yeah, same thing that happens here. The 1 is really comes from all possible arrangements divided by 2 to the 6th.
Is the long way to do this by doing like the casework for 1 and then 2 and then 3 and then 4 and like so on?
Nice. Yeah. So you'll see. Let's do it. So this is going to be 1 minus 1 over 64, which is 63 over 64. Okay. Lachi, let's do the long way. Let's try this another way. How would you set it up?
The probability of having one girl plus
So I'll
the
say,
probability of having 2 girls.
yeah, I'll just say probably of, when I say one girl, I mean exactly one girl. So probably of one girl plus probability of 2 girls plus probability of 3 girls plus and so forth, all the way to probability of 6 girls. Okay. Now you'll see in a second, this is something really nice that hopefully you'll recognize. What's the probability of exactly one girl?
1 over 64.
Not just the, that's if it's going to be.
Oh, wait. No, it's 6 over 64.
Exactly, because you got to account for where that one girl is. So you got to do 6 choose 1. So it'll be 6 choose 1 times 1/2 to the 6th plus 6 choose 2 1/2 to the 6th. And it keeps going. And the last one will be 6 choose 6 times 1/2 to the 6th. And we saw earlier that the sum of the row in binomial theorem in Pascal's triangle adds up to 2 to the n. But this is the same row, but it's just missing the first case. So if you actually do all the numbers, you'll get exactly what you want. You'll get 63 over 64. But yeah, so for when it's this type of question, at least or at most, and there's only like one case versus a bunch of others, it's much easier, like Olivia suggested, to just focus on that one case rather than thinking about directly adding up, okay, at least one girl means one girl or 2 girls or 3 girls, or like exactly one girl, exactly 2 girls, exactly 3 girls. Okay. Any questions on this example? All right, let's do, so what we've done so far, we're just gonna mix it up a slight amount, and that will get us to a really nice idea. And then at the end, hopefully by this lesson, you'll actually see that you already learned this whole idea. You learned this whole thing before. It was just called something different. So that you're not really learning anything new today. You're just relearning something that you've already seen in different clothing, basically.
It kind of looks like binomial expansion to me.
Exactly. Yes, that's exactly what it is.
Cool.
And I'll show you how you'll see it exactly like binomial example. This one, it's kind of hidden. And the reason it's hidden is because it's 50-50. But let's do a case where I'm going to do this example for a while. So, Shaq is known for being a great free throw shooter. He has a 30% chance of making the free throw or foul shot. Those of you who aren't familiar with basketball too much, this is when a foul is called or some sort of penalty. Shaq can go up at the foul line and he can take a shot. And we assume that he has a 30% chance of making a foul shot, and each shot he takes, and this is actually, I think, if you look at the basketball data, I don't think this next statement is true, because I think there's some likelihood if you miss the first shot, you might readjust and make the second shot. But let's assume that each shot that he makes is independent of the last. So here's a question. Write an expression let me back up. So if he takes 7 shots, I'm not going to do 7. I'm going to do 5 shots. What is the probability that he makes exactly 2? Two of them. Okay. And I'll give you guys a little bit of time to think about it. Alex's idea was really good. The observation that this is really something that you guys already have learned. So see if you can kind of put these ideas together. And just give me the expression. We can calculate the number once you have the expression, maybe plugging it into Google. But for now, I just care about the expression. All right, so some of you are very close. This one is not a 1 minus 1. This one, we're not going to look for a complement because like making 2 shots, exactly 2 shots, the complement of that is actually, you know, kind of complicated. So this is just like one sort of situation itself. You guys are having a great ideas. A few people got it. A few people are really close. I'm just gonna give you guys a few more minutes, and I'll keep messaging me though if you have ideas. If I didn't get back to you, you can always message me again. So this one's really, really similar to the one with the kids, but just has a slight twist to it. Oh, happy birthday, Lily. Yes, have a good
Thank
birthday.
you.
Yes, bye. Okay, so um, Adam, would you be willing to share what you got?
Yeah, sure.
Go ahead.
So basically what I did was I found the odds of getting two foul shots out of 5 in a certain order.
Perfect.
Um,
Let's say specific
only,
order.
He makes the first 2 and then misses the rest of them.
Let's do maybe like hit for make. I don't know. Yes for he made it, and no for he didn't.
Yeah, sure.
So what's the probability of this one?
Well, that's I didn't actually calculate it, but it's 30.
Expression?
It's 0.3 times 0.3 or 0.3 to the power of 2 times 0.7 to the power of 3.
Excellent.
And then to find the probability of the rest of the situations where he makes 2 and misses the rest, you multiply that probability by 5 choose 2, which is the total amount of possibilities you can arrange that 2 y's and 3 n's.
Awesome. Perfect. Thanks, Adam. Very, very good. So there's going to be 5 choose 2 different ways to rearrange these different ways of getting exactly, that's one other way. There's a whole bunch of them. And maybe you can do probability of no, 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 yes, yes. And each of them, because they're independent, they're always going to be 0.3 squared times 0.7 to the third. And if you were to visualize this as a tree, where each branch in this tree is either 0.3 or 0.7, you'd see here that you're talking about branches with 2 0.3s, like 2 copies of 0.3 and 3 copies of 0.7. And then you're just going to add up the probabilities of all of those branches. Excellent. So the final answer is 5 choose 2 times 0.3 times 0.3 squared, sorry, times 0.7 to the third. Okay. Anyone is able to calculate what this number is, just out of curiosity? What is it? 10 times 9 times 243, and then you got to get the right decimal.
I got 0.3087.
0.3087, okay, nice.
Yeah,
So,
same.
Cool. So 0.3087, cool. Neat. So what do you guys think? How does this compare to binomial theorem? Do you guys see that this is really just an expansion of the term with two shots where two yeses, I guess? It's the same as the expansion of 0.3 plus 0.7. If you want, you can even put a variable in front of it. If like it's not necessary, but you could even do like a y and the n here. If you do the expansion of this to the what is it, fifth power, you're going to get a bunch of terms, and this one is just a specific term in the expansion. This is the one where you have exactly 2 yeses or 2 0.3s. And what's neat is if you completely erase the y and n, like, what's the chance, if we were to do this problem, what's the chance of him making exactly one of them? You could do that problem. You can do exactly making 3 of them, exactly 4 of them, and so forth. You could do each of those and add them together, and you should get 1. And if you look at where these numbers are coming from, is it clear that everything should add up to 1? What's the expression on the very left? It's just 1 to the 5th. So this is, you get a whole bunch of fancy numbers, but really they all add up to 1. So I'm just going to write out the expansion. This is 0.3 to the 5th. This is he makes all. He makes all of them. Plus 5 choose 1. 0.3. Oh, sorry. yeah, 0.3 to the fourth times 0.7 to the first. This is he makes exactly 1. Oh, sorry, makes exactly 4. And then you keep going down. So plus 5 choose 2, 0.3 to the third times 0.7 squared. And we did 5 choose, next one will be 5 choose 3, but it doesn't matter because 5 choose 2, 5 choose 3 are the same. So this one he makes 3. Okay. Any questions? Oh yeah, the shack making 30, the 0.3 comes from the shack making 30% of, has a 30% of making an individual foul shot. And the other probability is 1 minus that, 70%. All right, any questions on this example? So let me give you a similar one where you can use the complement. You don't need to do a somewhat complicated situation calculation. So same setup. If Shaq takes, why am I lowercasing it? He definitely needs to be uppercase. He's Shaq. If Shaq takes 7 shots, what is the probability? In a lot of these problems, it's really about reading it and carefully determining what it is actually asking. What is the probability that he makes at most, this time it's at most 6. That's right. I like it when Shaq is in the car commercials and it's like a huge car, but it still looks tiny for him.
Are we using the same numbers from up above?
Yes, same thing, 30% of chance of making it and 70% chance of not making it. Nice. Chester, do you want to share what your idea was?
Yeah, so basically I just kind of like did the faster way for this. So like subtracting from a whole number, which is 1, and just subtracting the one possibility, which is not going to happen, which is 0.3 to the 7th power.
Excellent. So probability of, this is like an at most at least problem that's really close to like almost everything. Sometimes you can't do this shortcut if it's not like, or sometimes it doesn't make sense to do this. But probability of at most 6 is 1 minus probability of he makes all 7. So it's kind of annoying to do at most 6 because that would be, doesn't make any all the way to make 6. But instead we can do the complement. And what probability did you get for that one? For the probability that he makes all 7?
The probability of, hold up, I didn't find 0.3 to the 7th power, which is
Perfect. I think that's going to be a pretty small one.
it's a really small number. It's 0.0002187.
Nice. So some tiny number. So basically it's very unlikely for him to make all 7 shots. So he's definitely almost guaranteed, almost 99.9% chance or even higher than 99.9%, right? Chance that he makes at most 6. Okay, great. So I'll just tell you what this is called. What we learned today is called binomial probability. And that's when you have, so when you conduct, this is the fancy way of saying it. When you conduct, and let me just cut and put this is binomial probability. And we're going to return to this again. So for now, it's just going to be like understanding this idea with the complement and how to do a basic problem. But we're going to return to it and kind of investigate this what we call probability distribution in more depth a little bit later on. But you guys did really great with this. So when you conduct n trials of a experiment, n trials of an experiment that, oh, and I should definitely write here n independent. This is the key idea. So you have n trials, or like n attempts of an experiment that has a probability of success is equal to P, and probability of failure is equal to Q, which is the opposite. If you fail if you miss the shot, it's 1 minus 30%. It was 70%. Then we say that the probability, so you conduct n trials of an experiment where each experiment has a success P and probability of failing Q. The probability of K successes out of n is the following expression. And I hope everyone will recognize this. It's n, choose k, p to the k, q to the n minus k. Okay. So take a moment. There's quite a bit of like different symbols here. Just read this over and see, make sure it connects with what we just learned and also what you previously saw. So please hit yes if you recognize that this is just exactly each term. What this is talking about is each specific type of term in the binomial expansion. That's all it's saying. And instead of using letters X and Y, we're just using complementary probabilities of success and failure, P and Q. And this is a really neat idea because it builds on two things. It builds on this fairly intuitive idea of, okay, if you have independent events with the same probability happening over and over, you can talk about the probability of one specific sequence. And then you can combine it with the idea of the combinations and say, well, if I don't care how that event happens, I just want to know the overall amount of like successes and failures. I need to account for the rearrangements, and that's where the combination comes in. And it's exactly like we did this exact type of very similar question. Instead of using 0.3 and 0.7, I think I plugged in we plugged in x's and y's, or 2x and 1 over x. You can plug in really whatever you want into binomial theorem, as long as it's just two things. Okay. Yeah, we'll talk about this more in depth, but when we get to the bell curve. But for now, this is a good starting point to be able to answer questions about probability. All right, guys. Are there any questions on anything that we learned today? All right. So for next class, please just go over those 10 questions, and we'll do them together in class if you have any questions. Last time I taught the course, I know a few of them were a little bit tricky, and I know students had some trouble with them. So I'll devote the next class to just going over those questions. And if we have some time, we maybe we'll do some other like interesting probability or like counterintuitive probability example. There's a lot of neat examples in probability where kind of like that one where I asked, like, if you have 4 kids, what's the chance of exactly having 2 girls, 2 boys? Where the answer, might not be exactly what you would first expect. All right, if anyone has any other questions, I'll be sticking around for a little bit, but otherwise, I'll see you guys on Thursday. Good luck deal hunting.
Thank you, Daniel.
See you. Bye. Bye, Kieran. Bye,
Thank you
Penelope.
so much.
Thank
Have
you.
a good day.
You too, guys. See you.
I have a question.
Yeah.
For late work, I got very distracted over the weekend with some involuntary volunteering, and the Khan Academy stuff totally slipped my mind. Is there
Okay.
anything I can do about it, or should I just turn it in late and get a reduced grade?
No, yeah, just turn it in. I'll give
Okay.
you full credit. Yeah, that's no problem.
Oh, okay. Thank you so much.
Yeah, definitely.